Right, okay, so can I just have your attention, please? Could you do me a favour and just switch off your computers? Just switch off the screens, because it's really difficult lecturing to people who are on their computers. So if you just turn them all off, that would be absolutely wonderful. Yeah, try and focus on what I'm talking about. So what I'm going to do is, this is basically, we've got lots of people arriving late. Just let them come in. So just grab a seat as quickly as you can, chaps. Don't switch on the computers. Leave the computers off. Just sit down. So this is like a lecture that Arthur gets me to give. I'm not really lecturing on this. Well, I guess initially I wasn't really lecturing on this course, but I spend my whole life doing solar materials. So I volunteered to do it. So this session was initially last year. It was a session of about 30 people, no, maybe 20 people last year. And they had the option to do this coursework. And basically, they all enjoyed it quite a lot. And Arthur said, well, why don't we make it compulsory for the whole module? Because they all enjoyed it quite a lot. So I sort of view this as like a fun activity. And the coursework is set up so you effectively get a high mark for it. So it's very, very easy to basically pass it. What I'm going to do is I'm going to effectively tell you how to do the coursework and tell you how to get the marks. So this is going to last for like half an hour to 40 minutes. I've not delivered this before, so I'm not quite sure how long it's going to last. And I'm going to take you through the coursework question by question by question, and I'm going to give you the answers effectively. And then what you're going to do is you either here or at home, you're going to go away and use the CAD package basically, and have a play and have a bit of an understanding. So it's going to be a bit of lecture, a bit of practical, then a bit of homework. But basically, if you listen carefully, I'll give you all the answers. The other thing is I'm basically recording this lecture, so I'm going to put it on YouTube. I think I'm going to put it on YouTube because these university cameras here are really terrible at recording. So you'll have the video with you when you do your coursework. So hopefully that should help you also get the high mark. Okay. So this is called Introduction to Modeling Solar Cells. So let's go. What is this tutorial? Basically, it's a very brief introduction to modeling solar cells. It will give you a basic understanding of how solar cells work, so the actual sort of physical principles behind them. And it's aimed to give you basically some general ideas of their operation, like very, very broad brush ideas of their operation. What it is not a semiconductor physics lecture. So, you know, if we're starting, you know, an MSc course in semiconductor physics, we'd dive off into Fermi levels and things like that. But we're not even going to really mention Fermi levels. How many of you got a good background in semiconductor physics, by the way, out of interest? Anybody? Have you done any semiconductor physics modules? One, okay. So it's basically aimed for everybody but you. So sorry about that, but I hope you find it interesting anyway. So this is what we're going to go through. I'm going to look at motivation. Why am I going to teach you about modeling solar cells? Like, why do I care? Why do I think 100 people should understand modeling solar cells? Well, we looked at some of these graphs last lecture, this sort of exponential growth of basically solar cell production. You know, this is year and this is the log scale. So solar cell production is just going logarithmically up. They're becoming ever more important in our lives. And do you remember us talking about the concept of peak oil and peak coal and how we have to figure ourselves out of this concept? And I showed you the graph of basically global oil production. And I said, you know, at some point it's going to go down, but we've discovered fracking. I dug up the graph for UK oil production. So actually, UK produce a lot of oil, and until very recently, we're actually a net exporter of oil. And this is the UK's oil production. So we basically got a big bump in the 1980s, and a bit more of a bump in the 2000s, and now all the oil fields are just declining. So that's just a microcosm. The UK is just a microcosm of the world. At some point, the rest of the world oil production will just decline like this, and there's nothing we can do about it. So that's the motivation. So basically, what I want to say is, solar cells are going to affect you as engineers or scientists or managers or whatever. You know, you're going to come into contact with them, so you better know a little bit about how they work. So you can even make design choices. You know, like, should I be buying this system? Should I be buying that system? Even at the very basic level. So that's what this is really aimed at. And also, it's meant to be quite interesting and fun. So the structure of modern solar cells. So effectively, people have been developing different types of solar cells for years and years, and the general thing you say about all these solar cell structures is that they consist of basically different layers of materials. You can say that generally speaking. So here's a silicon solar cell. It's got various layers of materials. Here's some organic solar cells. It's got various layers of materials. Here's a solar cell where various layers optimized to absorb different colors of light. And if you look at this sort of I'll go to the next slide. If you look at this expansion here of this perovskite solar cell, it's got a glass substrate. So what's the glass substrate for? Keep it nice and stiff. It's got some contacts, what they're for, conducting electricity. It's got a bit of material that absorbs the light, so that's going to be optimized for absorbing light. You've got another bit of contact here. So each one of these layers has basically got a special property. So you can think of a solar cell as like a double-decker sandwich or a cheeseburger with like lots and lots of different layers. And each layer sort of does something specific. And what we'll do is we'll have a go at sort of modeling and changing these layers and see how this affects the solar cell performance and how it changes its basic absorption of light. So this is question one. This is how useful this is going to be for you to get your marks. Look at the image of the solar cell, so that one. So this will be in the CAD package. You can see it split into 4 to 5 layers. Each layer has a name associated with it, ITO, P.PSS, etc. Write down what each layer does of the solar cell and where possible find images of the chemical structures and place these in reports. So there's a little bit of Googling. Put each one of those things, ITO, P.PSS, P3HT, PCBM, aluminium. I'll give you 2 of the answers right now of what they do. Aluminium, that's a contact, it's a metal. P3HT, PCBM. P3HT is a polymer, it's a bit like sort of plastic. And PCBM is like a sort of a football made of carbon. And its job is to basically absorb light and conduct electricity. So that's the light absorbing layer. That's called the active layer. And I'll let you find the other 2 layers. So there you go. You got like 5 marks for that. So this is going to be quite practical. So we're going to be downloading software, installing software, having a play. So firstly, we're going to talk about downloading and installing the software that we're going to use. So I'd like you to download the software from here. So I've put it on GitHub. Just because it's got lots of bandwidth, and download it from here. GitHub. Just click on this link. I'll put this link up in a minute. So github.com, Roderick Mackenzie, GPVDM release 5.1, and basically I just don't want you all hitting my little web server. So you can find the software in other places, but my server that hosts it hasn't got much bandwidth. So if you could download it from there, that'd be fantastic. Then it comes down as basically a zip file. So basically you want to unzip it. And do you want to know how to unzip archives? Yeah, anybody a bit confused with that? Well, if you're a bit confused about downloading and unzipping archives, just shout and I'll help you. But basically once you unzipped it, you get a folder like this with lots of sort of DLLs and executables and things. You want to copy this into your desktop directory. So you want to literally copy this folder or whatever is in the archive to your desktop and run it from there. And then you double click on this executable called gpvdm.exe, and that's called General Purpose Photovoltaic Device Model. And there's one there called gpvdm core. Don't click on that. Click on that one there. It's very important. So this is a really important thing I should mention. It uses the model uses a lot of disk, so it accesses the disk a lot. It writes loads of files to the disk. It reads loads of files from the disk. If you try and run it off your Z drive, so a network drive, or a USB stick, or a hard disk, or anything that's not the hard disk of the computer, it'll be really, really slow. So make sure it's on the desktop or on the C drive or somewhere where it can access that hard disk fast. Obviously, the simulation and also the simulations, don't save them to a USB stick, save them to the hard disk, save it to the C drive because it does lots of reading and writing. But obviously, when you finish your work, copy those simulations off onto your Z drive so you can save them. But basically, run the simulations locally and copy them away to save them. And that's it. So once you've double-clicked on it, it'll ask you to register. So just fill in these boxes. And then we'll run our first simulation. So you get this window up, basically, that looks like this. And what you want to do is click on New Simulation, so it's got a 1 by it there. And then you want to double-click on Organic Solar Cell and then click Next. And so we're going to be simulating an organic solar cell. So this is a type of solar cell that's very sort of research active at the moment, or quite. There's lots of people interested in any case. So we're going to be sort of having a real play with modeling that type of solar cell. So you can basically use the mouse to look around this picture. This is like a virtual sort of CAD model of the solar cell. You sort of drag and move it and look at it in all directions. And there you can see sort of the layer structure, that sort of this sandwich structure of the solar cell. Then you click play and run simulation, and you get this up. It'll just run the simulation for you, and you'll get this bar at the right-hand side. Lots of text will scroll up. And effectively, I think the red CPU and the blue's disk. So if you can see which is holding back your computer, if it's the CPU or the disk, and that scrolls down there. Yeah, red's disk usage. Then we look at the output. So it's that simple. So it's run, and we just click on output, and double click on JV.dat. So JV is the current voltage curve. So we talked about current voltage curves of solar cells. JV dot is just literally the current voltage curve of the diode. So how many of you have how many of you are electronic engineer type people? Okay, so quite a few of you, most of you. So if you've ever looked at the diode equation or how diodes work, all this really is a glorified diode simulator. We're actually simulating the diode itself. And this is literally a current voltage curve that you get from the diode. Notice it's slightly negative because it's in the sun and the solar cell's generating some electricity. So again, going back to the last lecture, and we've got these various points on our curve that are important. There's VOC, which is the open circuit voltage. That's the maximum voltage it can produce. We've got JSC, which is the short circuit current. So that's the maximum current it can produce. And we've got I put a sign on the door saying if you're late, you go and use the back door. So there's a person there. And this is the maximum power point. So if you think about applying P equals IV, so IV across that curve, you can think where the maximum power is going to be. So here the J, which is current, is basically zero. It is maximum voltage is zero, so no power. Power increases up to P max, and then at this point here, the current goes to zero and the voltage is the maximum. So again, no power. So this is the maximum power point. Then it also kicks out this file called SimInfo.dat. This will tell you all about the parameters of the solar cell. So its efficiency, it'll calculate. So you could, from this curve, like look at this curve and squint and find out what that voltage is there and what that current is there. But the model will calculate that for you, and it spits all that out in this file called SimInfo.dat. And when you open that, you basically get a chart with a few bits of information in it. So it's got the power conversion efficiency, so that's how efficient it is. So it's 4% efficient. It's got the open circuit voltage. It's got the short circuit current and a few other bits and bobs in there. So that's all tell you about what's going on in the simulation. So question 2, what is JSC, what is VOC, what is fill factor of this solar cell? How do these numbers compare to a typical silicon solar cell? So I've probably actually just, if this I'm not quite sure if this is actually the correct solar cell that you're meant to be modeling. I'm not quite sure if these numbers are correct, but if these numbers are correct, you can just read them off here, and that will be your answer. But I do the simulation myself because I'm not sure that is the correct answer. And so how do these numbers compare to a typical silicon solar cell? And I said, well, use the internet to find out these values. So what you do is you look up the typical values of a silicon solar cell and compare it to its organic solar cell, and you say, oh, which one's better or why? And then think about why that might be, or maybe Google will tell you why that might be. So that's question 2 of the coursework. So I'm not giving the answers, but I'm sort of massively pointing in the right direction with this coursework. So I hope you find it's useful. So now we're going to look at varying active layer thickness. So what I'm going to do now is tell you some fundamental things about solar cells that are pretty useful. So we're looking at varying active layer thickness. So this here is the active layer. This is the bit that basically absorbs light. This is the bit that does the magic. This absorbs photons and it turns them into electricity. So if we vary the thickness of this layer, it should have an effect, right? It should change the device. So we're going to try and understand that. And before we get into this, just to sort of key you up in terms of thinking about it, if you think about the active layer thickness, it could be a very important parameter for cost, because the thicker that active layer is, the more material you've got to sort of buy to make that layer. So you have a nice thick layer, it might be a really good or bad solar cell, but you've got more material in any case, so it's going to be more expensive. And the thinner you make that layer, the cheaper it will be. So there's cost implications of varying any of these layer structures. And also, importantly, to make any of these materials, you need to basically burn coal. So there'll be CO2 implications too. Some of these layers require a lot of CO2 to make, so lots of energy to make. Some don't require much. If you think about making aluminium, you get lots of bauxite, and you use electricity to sort of melt it down at 600 degrees C. So that's probably quite an energy-intensive process. So changing the thickness of these layers by double or 3 times can really affect the CO2 that you use to make these solar cells. So what we're going to do is look at the layer editor. So this basically changes the thickness of the layers. And effectively, it's got the layer name, which is sort of what the name of the layer is. It's got the thickness of the layer. It's got what the optical material is, and a few other bits and bobs that we don't need to worry about today. So these are the values. These are the thicknesses of the layers in meters. So 1 times 10 to the minus 7 meters. So how many microns is that? How many microns is that? We're talking nanometers, aren't we? Talking nanometer materials. So this is 2.2 times 10 to 7 meters. So we're talking 220 nanometers. So if you think about the width of a human hair, typical width of my hair is between, so I got this on Wikipedia, 70 microns to 181 microns. I don't know how they know the average is 281. That seems very accurate to me. So human hair is way thicker than these layers. Like, you know, we're talking maybe these layers are 100 times thinner than a human hair. They're super, super, super thin layers. So question 3. Oh, so what you can do basically is by double-clicking on these layers and changing it to say 2.3, 2.4, 2.5, whatever, you can change the thickness of those model layers like this. So you sort of make these layers bigger. It'll show up in the model, and then what you can do is run the simulation again and see how that affects efficiency. So you can basically double the thickness of this layer and then see how that changes the efficiency. So is it worthwhile to make that layer nice and thick? So here we go. Plot a graph using Excel or any other graphing tool of device efficiency versus thickness of active layer. What's the optimum efficiency stroke thickness of the active layer? Also plot a graph of VOC, JSC, and fill factor as a function of active layer thickness. So what we're doing is I'm going to try and get you to understand how the thickness of these layers affects device efficiency. So all you're going to do is basically, well, I've said this before, but all you're going to do is effectively vary this number here over, say, a few nanometers, and see how the efficiency, see how VOC, see how fill factor, see how JSC change, and you get a real understanding of, sort of how that layer thickness affects the efficiency of the solar cell. And basically pull those numbers off and put them into Excel and just plot a graph. And you know, might need to run 10 simulations to do that. Yeah, okay. So, solar cell spectrum and material choices. So that is a picture of the visible region of the sun's spectrum. So what somebody's done is they've got a diffraction grating, got the sun's light coming in, and taken a picture with a CCD camera of the sun's light. And all these little bars here are sort of absorption in the atmosphere. So it might be water, or it might be a bit of oxygen. So all these little black bits, that's actually absorption of the sun's spectrum. And if there's no atmosphere, it would probably look more like a perfect rainbow. So let's think about this. We've got the sun spectrum coming in here, but we want to have an optimum material to absorb the sun spectrum, because this is the point of a solar cell, is to absorb light. You know, it's to absorb light and turn it into electricity. That's the point of a solar cell. So is there a perfect material to absorb this light? Let's try and think about it. Well, let's try and plot the sun spectrum first. So we can get the sun spectrum out of the model by, if you go to the Databases tab, click on Optical Database, and then double-click on Sun. It brings up this graph, and you can see this is actually the sun spectrum from sort of 4,000 nanometers down to sort of 300 nanometers. So if we zoom in on that, so here's sort of a bit blown up. This is the region, this sort of, only here is where we see. That's what we see is our human eyes. This is the bit that burns you when you lie on the beach too long. This is all the UV stuff. And this is all infrared stuff down here that you can't see. It's just sort of heat. It's sort of a long wavelength heat, effectively. So, so question 4, describe the main differences between the light which comes from the LED. So if you look at this, if we go back, you see in here I've got something called LED. That's a light emitting diode. That's like it's like a standard white light emitting diode that I've pulled off the internet. And So I say, describe the difference between the light which comes from an LED and the sun, rather than referring to variations, the various regions of the spectrum by their wavelengths, refer to them with English words such as infrared, ultraviolet, red, green, and blue. So I want you to effectively take the sun spectrum, which is that wiggly curve, and then look up what colours, which wavelengths are which colour, and then compare it to an LED and say, oh, the LED emits more green light, or the LED emits more blue light, or whatever the answer is. I can't remember what the answer is, but just compare those spectra, just to get the idea that basically different light sources are very, very different. And artificial ones almost certainly won't have all of this infrared stuff, because that's just wasting energy if you want to light a room, because we can't see it. So now let's look at materials. So let's try and answer the question basically, what material would best absorb the sun's energy? Like, should we make our solar cell out of glass? Well, probably not, because we can see through glass. That's not going to be very good at absorbing the sun's energy. Maybe we should make it out of something sort of black, because that absorbs energy very well. So different materials have different absorption spectra, basically. So if you click on the materials database and then double click on polymers, so the solar cell we're looking at is a plastic solar cell. Its advantage is it's basically it's very, very flexible, and it's meant to be quite low cost. So they're made of effectively conducting polymers. So if you click on the polymers box, you can see some various types of polymer, and you can click on some, and what we can get out. So in this case, I've clicked on P3HT. I get the absorption. So absorption material is how many photons it absorbs. So it's like, it's like this. Here's a liquid absorbing a laser. That's absorption. And it's also got a refractive index. So this is refractive index. And a refractive index is effectively the thing that bends light as it goes into glass or into a pond, or why fish can see you quite easily from a pen. So the material's got these two key properties. It's got absorption and refractive index. And by looking at these tabs, you can see basically what the absorption and refractive index of this material look like. So, question 5. What colour does the polymer P3H2 absorb light best? Which material in the polymers directory do you think will absorb the sunlight best? So, well, I'll give you one answer to the first one. There's the absorption. Where do you think this material absorbs the light best? Let me shout out. Where do you think it absorbs light best? 500, exactly. It's at 500. And I want you to basically search this directory, have a little look at all these materials, and have a think as to which one you think is going to absorb the sun's energy best, and come up with a little argument for it. Like, why is this? Maybe one material absorbs very well the most energetic part of the sun spectrum, where there's most energy in the sun spectrum. Have a think about it. So performing optical simulation. So light is important to solar cells, basically, and how light interacts with a solar cell will depend how efficient it is. So what we can do is we can do optical simulations. We can we can model how the light hits the solar cell and how it interacts with it. And we can do this with the optical simulation tool. So basically, you click on Simulation, Optical Simulations, and you click Run Simulation. And what it will do is it will model the light propagating in the device. It will literally model all the colours of light propagating in the device. And you can think of each one of these layers, basically, as have you ever done that wave tank experiment at school in physics, where you have that thing bobbing up and down, and then the waves come along the tank, and you can have it diffracting off various things? Anybody remember that? One person nodding. Everybody else seen that at school? Yeah. Okay. Well, this is about the same. It's the same idea. You've got the waves coming in. That's light. And you've got these various materials in here, the layers of a solar cell, and the light will sort of reflect off various layers, and then some waves will get through the first layer, and they'll reflect up and down between these two layers, and then some will get a bit further in, they'll reflect up and down those layers, and then the aluminium, it's just metal, it absorbs all light, and that's why the photons just drop off there. So you can have a play and basically change these layer thicknesses and see what the profile of the light looks like in that material. And it only looks like this with these waves because it's so thin. The materials are so thin they're comparable to basically the wavelength of light. And this is quite cool. You can plot effectively, this is position in the solar cell, and this is wavelength. And you can plot effectively wavelength versus position of where stuff's being absorbed. So you can say, oh, this material absorbed really well in this area of the spectrum, or really badly in this area of the spectrum, and you get a real feel for like where the material's absorbing stuff. So if you're going to design a new material, you could be like, oh well, what we should really do is have it absorbing light in this region, or another region. Then if you double click on SimInfo, so you'll need this again. So this SimInfo file's always got the sort of the information from the last simulation in it. So if you double click on the SimInfo.dat, you get the number of photons absorbed in this active layer here. Now then, this is where it starts to get interesting. We've laid the foundation basically to do some interesting modeling. So now we're going to sort of look at the physics of how this works a little bit more. So by running 5 or 6 active layer thicknesses, plot a graph of active layer thickness versus the number of photons absorbed in the device. At what thickness do almost all photons get absorbed? So what we're doing is we're going to be varying this active layer, this thickness of the active layer, like this. Okay, and what do you think is going to happen as the active layer gets thicker and thicker and thicker? What's going to happen to the number of photons absorbed? It's going to increase, exactly. So we're making the active layer thicker, we're going to absorb more photons. Does that sound like a good thing? What do you think? Does it sound like a good thing, absorbing more photons for a solar cell? Probably, but it might cost more, right? That's what you're thinking, potentially. Yeah? Okay. But, thank you for taking part. This is a horrible room to lecture in, by the way, because you're all like crazily back there, and you're stuck behind these computers. It's really difficult to sort of interact with you all like this. But anyway, we'll carry on. Yeah, so that's the first bit. So the first thing, what we're going to do is study effectively making this solar cell thicker and thicker and thicker, and seeing it absorbing more and more photons. Now this is the clever bit. Now we're going to look at recombination. So I hinted before, the thicker the layer, the thicker the device, the more expensive it's going to be. It's going to absorb more photons, and it's going to be more expensive. But there's a slightly more subtlety to this, and we're going to look at that now. So let's think about this. Here we've got our solar cell, we've got a box, and we've got a positive charge and a negative charge, and we've got a photon coming in that's generated. We've got a photon coming in, it's generated an electron in the hole, and the hole will go one way, and the electron will go the other way. We've got charge, fantastic, photo generation. Now, think about this scenario. Imagine we've already got a hole here. So this has just been generated previously, it's just like hanging about in the device. What would happen if these two met? Well, a positive and negative charge combine, they destroy each other. They just disappear, basically. And what we're left with is just one electron. So this process, so I'll just go through that again. So we've had effectively a photon coming in, all well and good. It's generated a hole and electron. But unfortunately, we already have a hole in our device, a positive charge hole in our device, because it was there from being generated previously. These two now meet, and they annihilate each other, and we've lost our electron. Well, not only have we lost our electron, we've also lost our hole. And now we've only got one charge carrier. This is called recombination, because two things have gone together, and they've recombined, they're gone. So this is not good. This is not good for solar cells, because obviously we had 2 charge carriers that could have made current, but now we've only got 1. And worst case, this meets another negative charge, and then we've got none. So if photons come in, and we've got no electrons out to our circuit to drive our motor or whatever it is we want to drive. So this is bad. Recombination is bad, because it means you're wasting photons. You put a photon in, you generate electrons and holes, and they've just gone, because they've met other electrons and holes. Now, question is, how can we avoid this process? So we've generated. So let's go back to our picture. We've generated our electron hole here. We're going to have these other charges around the device because we've got loads of photons coming in anyway. So how can we make sure this gets to contact really quickly, this gets to contact, and they don't recombine? The way we do this is to try and get this electron hole out of the device as quickly as possible, like really, really quickly, and then hope, because they're out of the device so quickly, they haven't had time to meet any of these holes. I guess it's like speed dating or something, you know. If you sort of leave really, really quickly, they're not going to meet. So the concept is, after photon generation, get your electrons and holes out of the device really quickly, and they won't recombine. So this is how we define recombination mathematically. So we've got an electron, here we've got a hole. The rate of recombination is equal to a constant times the density of electrons times the density of holes. So if you've got lots of electrons, lots of holes, and we'll forget about the K, you get a big amount of recombination. Not many holes, not many electrons, you get a small amount of recombination. And this K is just a number, it's like, it's between 0 and 1, say. And it just says how efficient this process is. So if this is the rate at which electrons and holes are meeting each other and recombining, do you want a big or a small K for your solar cell? If you want a really good solar cell, do you want a big or a small K? Small. You want a small K because you want recombination to be 0. So, these are some silly questions. In no more than 2 sentences, describe what an electron and hole are. And I'll give you a big hint for this coursework. So you can do that. I've just told you it's positive, negative charge. I'll give you a big hint for this coursework. Don't write much. Do not write a page. We're not interested in a page. Try and limit your answers to like 40 words. You can get all answers in like 40 words. Do not write essays, please, because Arthur's got to read them and he'll kill me. Plot a new graph of active layer thickness versus device efficiency. By looking at your graph, what's the optimum device thickness for a device with a recombination constant of K times 10 to the minus 15? I'll show you where to set that. But basically, you put this value in. We've now turned on some recombination, and we're going to replot this graph. So what's going to happen? Right. So what's going to happen basically is as the device gets thicker and thicker and thicker, you're going to absorb more and more photons, right? But as the device gets bigger and bigger and bigger, it's going to take longer for the electrons and holes to get out of it. Because it's a bigger device, it takes longer to get out. So there's more chance of electron and hole meeting other electrons and holes and recombining. So as your device gets bigger, your recombination goes up, but you absorb more photons. So somewhere there's a happy medium. Because if you think about it, a huge device, there'd be loads of recombination and no electrons and holes would get out. A really thin device would have very little recombination. But then on the other side, a thick device would absorb lots of light. A thin device doesn't absorb any light. So somewhere there's a happy medium. And your job is basically to find it. So you're going to do a few simulations of device thickness and plot the graph of efficiency. And then basically you're going to find out the optimum thickness of the solar cell. Charge carrier mobility. So the other way we can basically get electrons and holes out of the device really quickly is to design materials that naturally allow electrons and holes to move really, really quickly. So imagine you sort of, so some materials have really low, and the parameter we assign to how fast electrons and holes can move in a device is called mobility. So a material with a very, very high mobility, the electrons can get out of the device really quickly and they don't recombine. But a material with a low mobility, it takes ages for electrons to get out of the device and they'll probably recombine. Before we move on to the sort of final thing, recombination can also be described as a time constant, tau. So tau is basically the time it takes, on average, for an electron hole to recombine. And if tau, so would you want a really big tau for a solar cell or a really small tau? So what, did somebody shout the answer? Who says small? Who says big tau for a good solar cell? Really, really slow recombination. Takes ages for electrons and holes to get it to recombine. Do you think? So I'll ask again. The bigger the tau, the slower the recombination. The smaller the tau, the quicker the recombination. Do you want a big or a small tau? Hands up for a big tau. Yay. Hands up for a small tau. Okay, fantastic. That's correct. So you want a big tau, so recombination is really, really slow. Now, I'll come back to that. So there's something called the mu-tau product. And mu is the mobility. That's how quickly electrons can move. And tau is how long it takes an electron to recombine. So mu basically describes how quickly an electron can get out of the device. And tau describes how long it takes an electron to recombine. So if you've got a massive mobility, the electrons can move really fast and get out of the device quickly, and a really slow recombination time, then you've got a really efficient solar cell. So mu and tau to be good, or mu and tau both being good means the mu-tau product is big and you've got an efficient solar cell. On the other hand, if your mobility is really slow, if it's like treacle for your electrons to get out your solar cell, and your tau is really quick, so you've got really fast recombination, you have a rubbish solar cell. But you can play them off against each other, so you can have a material with amazing movement of electrons and holes, but you can have like really bad recombination. You sort of got to get an okay solar cell. So mu-tau product is like a really famous measure of how efficient a material is for a solar cell. So make a fresh simulation. set both the electron and hole mobilities to 1 times 10 to the minus 6, and calculate the value of mu-tau product. So there's more detail on that in the report. Finally, I'm going to do this last slide, and then we're going to get on and actually do some simulation, do the course. A bit more fun than listening to me. Finally, I want to talk about parasitic components in the solar cell. We've been talking effectively about this ideal solar cell, so it's like a perfect solar cell until now. But unfortunately, solar cells have other things going on, and they've got some resistance because they've got some contacts, they've got some material on the contact, got some resistance there. And you also got some resistance sort of in parallel with the solar cell, which is effectively impurities in the material. And these are represented, because we're all electrical engineers, as effectively resistances. So you've got R series and R shunt. You can set these in the model by using this parasitic components thing, and you can just pop the values in there. Shunt resistance should be about 1 million, and series resistance should be about 20. And you can effectively, with those parameters, they're basically, the shunt resistance is responsible for this part of the dark JV curve, and the series resistance is responsible for this part. And the final question is basically make a fresh simulation and have a play with those. And hang on, question 13 to 14 don't do. I've cut them out, so to make it a bit shorter. So last year they got to do a literature review, and I got them to do question 13 and 14 as well. We're not going to do that this year. So that was like a really quick explanation of what you had to do. Could I ask you now, please, to all turn back on your computers